welcome everyone. I'm just waiting for a few students to change over. Getting towards the end, so I just wanted you. Can you do a Maclaurin series for this, please? Go, do it. I want a Maclaurin series for that. See if you can write a Maclaurin series for f of x equals to ln x.
This Maclaurin series often asked in the exam.
Yes, every year.
And Taylor series.
Either one or the other. But Maclaurin series and Taylor series are the same thing, as we'll find out tomorrow. Yeah. The Maclaurin series is general about x equals to 0. The Taylor series is the Maclaurin series is about the point x equals to 0. The Taylor series is general about any point x equals to a. So the Taylor series is general, the Maclaurin series is specific to a point. Okay, has anyone screamed out to me yet? Mr. Stewart, I've got a problem.
Yeah.
What's your problem? Guess what? There is no Maclaurin series for that. Did you know teachers are getting free coffee? Mr. Stewart's in heaven. Yeah, we get free coffee in Kilmore. Isn't that good? Not that I drink cafe coffee anyway, it's too strong. As you can see, it's very strong. If I start laughing spontaneously, it's because I've had too much coffee today. Yeah, that doesn't work, does it? Why? Because straight away you can say to yourself, well, at x equals to 0, it's undefined anyway, isn't it? So straight away, you can't have a Maclaurin series for that because Maclaurin series is accurate. It's most accurate at x equals to 0. This function doesn't even exist at x equals to 0, let alone on the other side of x equals to 0, on the positive side. So, but as Brian found out straight away, of course, what's the first step in finding the Maclaurin series is to find the first derivative. And if you find the first derivative, f dash x, you end up with 1 divided by x. And then, of course, what do? You're going to go f dash 0, and all of a sudden you say to yourself, that's undefined. So we're in problems straight away. And logically, that's why it's undefined there, isn't it? So what do they do when this is in your data booklet? Rather than provide you, and it's well worth us doing that, with the Maclaurin series for ln x, they provide us with the Maclaurin series f of x equals to ln x plus 1. To counteract that, because tomorrow we're going to look at the Taylor series. And what the Taylor series does is it simply takes the Maclaurin series and it does a horizontal shift. Yeah? So we can shift a Maclaurin series from x equals to 0 to wherever we want. I can shift a Maclaurin series to x equals to 1. What do I need to do? I need to find f of x minus 1. Anyway, we'll worry about that tomorrow, but what this means is I need to work out a Maclaurin series for ln x plus 1. So basically what we can do is we can find the Maclaurin series for ln x plus 1, and then we can shift that wherever we like. So we need to do this now. Go, see if you can do it. Find that Maclaurin series. Write it as a series for ln x plus 1. This is in your data booklet, so it's well worth us actually running through that. And then I want to talk about for what values does this converge. I might do it as well because I need to practice this. So let's go. What's f of 0? I think you can start to see the pattern, can't you? Alternating? Yeah, because that negative, this -1 gets times to make, yeah, a negative and a positive and a negative, so it's alternating. What does it look like though? Look at this here. When that's the third derivative, it's 2. When it's the fourth derivative, it's 3 factorial. When it's the fifth derivative, it's going to be 4 factorial. Excellent. So I think, hopefully some of you can already see, this is going to form a Maclaurin series that looks something like this. F of x is equal to, first term will be x, second term will be minus x squared on 2 factorial, third term will be plus 2 factorial times x cubed on 3 factorial. Next term, Vincent? Diana? What's the next term?
-3 factorial times x to the power of 4.
Very good. Next term. Plus. Yeah, you've got the pattern now, haven't you? Yeah. And of course that simplifies down quite easily, doesn't it? That simplifies down to this. F of x equals to x minus x squared on 2 plus x cubed on 3 minus x to the power of 4 on 4 plus x to the power of 5 on 5. Cool, huh? What?
How do the x, why the x is on the
Why? Why?
I don't understand how you get x squared on 2 factorial.
That comes from the Maclaurin series. What's the basic Maclaurin series, isn't it? It's 1, yeah, plus well, it's f of 0, isn't it? F of 0. Then the next term is plus f dash 0 x on 1 factorial, yeah, plus f double dash 0 x squared on 2 factorial. So, are you asking me about this term here? How did I get that term? Well, what's f double dash 0? F double dash 0 is minus 1.
Oh.
Are you okay? Yeah, sorry. So, how do I express that in some notation? Express that in some notation. In sigma notation. That's going to equal to the sum from, well, we could start at 1. Yeah? Let's start at 1, will we? Go to infinity. Why not? Yeah? Then we'll just go x to the power of k. Yeah? Hang on, we better put a sign generator in. Cool. Yeah? Good. Okay. For what values of x does that converge? In other words, for what value of x can I assume that this series is going to converge? In other words, I can only use this here for a certain amount of values of x. If it's not within that radius convergence or within an interval of convergence, it's going to diverge. But how can a Maclaurin series diverge? Well, let's just have a look at that. Now, unfortunately I don't have my computer here, but you guys have got your calculator, have you? Have you guys got your calculator? Good, because we can sketch this graph in a moment. But let's just quickly, for what values of this converges? How do I find for what values of this converge? This is like one big long question, isn't it? How do I find convergence of that series? What would I need to use? Ratio test. Very good. So I'm going to apply the ratio test to this. So let's apply this ratio test. And I'll change colours here because this is now finding convergence. How do I find that? It's the limit as k approaches to infinity of the absolute value, so we don't need to worry about the sign generator, of x to the k plus 1 divided by k plus 1 times by k on x to the power of k. That equals to the limit as k approaches to infinity of x divided by, well, it's x times by k on k plus 1. Now, by now, some of you are probably saying, oh, as this approaches infinity, what does this approach? Yeah, I could divide that by k, divide that by k, and divide that by k. And I think you can see that this limit is going to approach 1. So, for convergence, using the ratio test, what do we need it to be less than? It needs to be less than 1. Great. So what I'm left with here is, if we come up here, if we take that limit, we've got the absolute value of x times by the limit as k approaches to infinity of 1 divided by 1 plus 1 on k. That's simply going to equal to 1, it has to be less than 0. So the absolute value is less than 0. So basically, this series will only converge when x is trapped between. But that's not all. That's the what's my radius of convergence? 1, isn't it? Now, straight away, some of you are going to say to me, I know. Can it be equal to minus 1? What would happen if x was equal to minus 1? Well, this is my radius of convergence is 1, right? What's my next job, everyone? Is to determine the interval of convergence. How do I determine the interval of convergence? I saw some of you do this morning. The first thing is to let x equals to minus 1. But do I really need to let x equals to minus 1? No, I don't. Because if I put x equals to minus 1 in there, what am I going to get? Undefined. So I really don't need to check that side, do I? I definitely know that it can't equal to minus 1, so I'm not even going to worry about that. But yeah, you could show that. I'm sure if you let x equals to minus 1, where's my series here? If you let x equals to minus 1, you're going to end up with minus 1, you'll end up with a divergent series. So it will diverge. I can see that, because that'll just be 1 on k. And as we know, the sum of 1 on k is divergent. So what would happen now if x is equal to 1? If x is equal to 1, what do we have? We have an alternating series, agreed? Can you see that? So I'll just write that down just so you've got that. So if x is equal to 1, what does my series become? My series will become the sum to infinity of minus 1 k plus 1. That's just my alternating series. X becomes 1, so that's just 1 divided by k. That's an alternating series. What's the alternating series test? 2 tests. One is to show it's decreasing, and of course it's decreasing, isn't it? I mean, you all know from your physics that's inversely proportional. It's decreasing. What else does it have to show? At infinity, what's the term? 0. And of course 1 on k is 0 when k approaches infinity. So those 2 tests are just going to be very, very easy. Basically just show this. That is less than that. Okay, so it's decreasing, and the second test we know is this. So I don't want to spend too much long on this because we've already done that. That equals to 0. So basically for this ln x plus 1, the Maclaurin series for it is this. Yes, but does this function converge for all values of x? No. No, it doesn't. So this Maclaurin series, you can't put any value of x you want into, Vincent. It does not work. So what I want to do is I just want to show you graphically why that doesn't work. And you've got your graphics calculators there. Unfortunately, I didn't bring mine, so I can't data project this for everyone, but I can show a picture of it. Can I rub off over here?
No, but when x is 1.
Oh.
Yes, but when x is 1 parameter is 1.
I'm going fast, aren't I? I'll slow down. First of all, though, I might just draw the function ln x plus 1. What does ln x plus 1 look like, Vincent? Looks something like this. I always pick on you, don't I? Mr. Stu always picks on you. Let's sketch this one here. That's going to shift ln that way. So we'll shift ln over here. We know there's an asymptote there because we know it's undefined at -1. There's x, there's y. We know it's undefined at -1. Yeah? Let's sketch that graph in blue. Yeah? Here we go. Go something like this. Cool, doesn't it? Now, let's approximate that function. Yeah? Let's approximate that function by using one term. Yeah? So if I use f of x equals to x, what does the function look like? Well, I might just draw that in red. If I was just to use one term of the Maclaurin series, what would it look like? It would go like this. Okay. Clearly, it works quite well, very close to x equals to 0. Doesn't work so well out here. So let's add on two terms. Can someone please sketch the graph of x minus x squared on 2 and show me what that looks like? So one person do that. And Brian, can you sketch x minus x squared on 2 plus x cubed on 3 for me, please? So can you do that one? Don't know if that's all right. X minus x squared on 2. And Brian, can you do x minus x squared on 2 plus x cubed on 3? And let's have a look at what those functions look like. So here's the one, f of x equals x. Okay, that works okay around here, but it doesn't work at the extremes. Adding on more terms should give us a greater sense of accuracy. So Diana's got this one here, goes like this. So this looks really good here, doesn't it, Diana? It goes something like this. Goes really cool, and then it starts to come around. Oh, it's a bit more like this. And then it starts to diverge there, agreed? Yeah, so it's working. This is a quadratic, so it's coming up, matching this bit really well. That's really cool, but of course we know something's happening at when x, as x gets greater, than 1, what happens? My Maclaurin series does not converge anymore. So let's go to a higher order and say, maybe at a higher order it does. Let's sketch the higher order one. Have you sketched your cubic?
Yeah.
What's the cubic look like? Which one is it? The red one? Yeah. So, okay, this is how the cubic looks, everyone. Nathan, the cubic goes like this, actually. The cubic's quite good. It goes like this. It goes, cubic comes in, models that really well, but then, as soon as we get close to x equals 1, guess what? Wow, it diverges. Yeah? Why does it diverge? Why doesn't, no matter how many terms you start to add on, the Maclaurin series gets really, really, really accurate in here, but as soon as you're on the other side of 1, guess what? It diverges. So, adding on more terms, when you're beyond the value x equals to 1, is the Maclaurin series being more accurate? No, it's actually worse. It starts to diverge further and further away. The more terms you add on the other side of x equals to 1, does anyone want to plot the next one? You'll see it'll even diverge even more. Have you done the next one? Oh, you've got it all in one. So where's the fourth one? Where's the power of 4? I can't see that one. Oh, the green one. So x to the power of 4 is even worse, isn't it? It comes up here lovely, but then it goes like this. It goes like that close and then straight down there. It was even worse than the quadratic, isn't it? Does everyone see that? Adding on more terms is accurate within the interval of convergence. Yeah? So within the interval of convergence, it's accurate, the Maclaurin series. outside of the interval of convergence, it's really inaccurate. Does that make sense? So here's 1 here. So here's my 1. Here's my 1 here. X equals to 1. Yep. And here's x equals to -1. Ladies and gentlemen, in here, yes, adding on more terms and more terms will get you closer and closer and closer to ln x plus 1. If you go outside of x equals to 1, like here, x equals to 2, the Maclaurin series, adding on more terms, is diverging away from that. Interesting, isn't it? Pretty cool mathematics, isn't it? Ask questions if you're not sure what I'm talking about. Do you understand what I'm talking about, Xavier? No. Well, I'll explain it. Okay. This is a Maclaurin series for this. Yes. So that series represents that function. Agreed? Only when does it represent it? For what values of x does that series represent that? Yeah, only between -1 and 1. Yeah? What happens if you're at x equals to 2? The function, the series, does not accurately predict the function anymore. You are outside of convergence. In actual fact, normally I showed you yesterday, if you add on more terms, what happens? If you add on more terms, the higher the degree of the polynomial, the closer you get to the function. That only works if your function is convergent for all values of x. This function is not convergent for all values of x. Once you're outside of the radius of convergence, adding on more terms takes you further away. It becomes less and less accurate, becomes more inaccurate. So, if I add on the first term was this, f of x equals x. So I'm using my first degree polynomial to approximate that. And it does a pretty good job. Yeah? That's just f of x equals to x. It's a straight line. The straight line's not too bad. Maybe I need to draw this again, do I? Do you want me to draw it again? Do you understand what I'm saying? We've got ln x. Ln x is... Do you want me to draw again? You sure? So ln x is the blue line. The first graph is y equals to x. It closely approximates, the blue line reasonably well. The second degree polynomial is x minus x squared on 2. Yeah, that's a quadratic. And the quadratic that Diana drew went like this and it came down. It was actually quite accurate for most of ln x plus 1. Next week we plotted a cubic function. Cubic function went like that. Again, we're seeing around the point x equals to 1, once we're on the other side of x equals to 1, the graph diverges really, really far away from ln x plus 1. Yeah? And I think, did you have it up there to show Xavier more accurately, or have you taken yours down? Yeah, well you can just see there what I'm saying here. It's probably easy to see it on the screen. The blue line is ln x, yeah? The red line is the third degree polynomial. See how it only works really up to there and there. Yeah? It only really works between -1 and 1. When you're on the other side of 1, the polynomial diverges away from the function. It doesn't work anymore. Does that make sense? Very, very good. Cool. So Xavier, what conclusion can I make? What conclusion can I make? Once you're outside of the radius, once you're outside of the interval of convergence, does the series approximate the function? No. Yeah? The series will only converge to the function at least if you're inside the radius of convergence. Yes? As we'll learn today, in this period, there's another test. Do you remember I talked about the error term yesterday? Yeah? What must the error term become for the function to be truly representative by the series? Is the error term at infinity must be equal to 0. That's right. And that's what I want to talk about today. So really, there are two conditions I need such that this series represents the function. What's the first one? When must this series represent the function? It must represent the function only for x values within the interval of convergence. Okay? Do you need to know this? I doubt it. I've never seen any question like this at all. However, I think it's important if you look back over this textbook particularly, I need to show you this because it actually spends a little bit of time talking about this. Okay. The test we're now going to do is to also to consider this. We can say this series is exactly equal to the function if we're within the radius of convergence and if the error term at infinity is equal to 0. Then the series is exactly equal to the function. Anyway, let's talk about my error term today, can we? It's called the Lagrange error term. I just thought I'd show you that anyway. This series is in your data booklet. You do not need to know it. However, isn't it interesting? Yeah, you can see that not always will this series converge for any value of x. You can test and find what the series does converge to by doing the ratio test and then testing each end of the interval. And that's how Chapter 3 and Chapter 4 marry together. Because you can make a Maclaurin series and then they can ask you, for what values of x does that converge? And that's how they would marry Chapter 4 and Chapter 3 in the one question. Okay, let's move on to the Lagrange error and see how much of that we can get done today. Can I rub this off here? Okay. This is all in your textbook, by the way, so you can go back and refer to that, or yourself, you can watch the video after this class. So let's talk about the Lagrange error method. I think that's what it's called, is it? What's the next section? What's the next chapter called? Error term, is it, or what? What's it called? 4B, is it? Hang on. Did I have a name for it? 4D, 4C, 4V. Approximations to the Maclaurin series. Yeah, we've already done that first part. Okay, so we'll call this approximations. Approximations to the Maclaurin series. Yay! Let's talk about this. So far we've got a function, f of x. Yeah? And then what I've got is I might have a polynomial. So let's just do a polynomial of degree 3. So f of x is going to equal to a polynomial of degree 3 plus it's going to have some error term associated with it. And I'm going to call this error term Rn x. Now in this case, Rnx is the error associated with using a third degree polynomial. So what am I saying by that? What's a third degree polynomial in this case? A third degree polynomial generally would be this. A0 plus A1x. Yeah? So I'm just doing the Maclaurin polynomial, but I'll do it like this. F of 0, what's the next term? F dash 0 x divided by 1 factorial plus f double dash 0 x squared divided by 2 factorial plus f triple dash x cubed on 3 factorial plus, if I only go to 3, to a power 3, if I only go to a third degree polynomial, is this going to be exactly equal to the function? No, of course not. Why? There's going to be some error attached, agreed? We saw that yesterday when we looked at e to the x. So I'm going to put here on my error term. Now, what I do is I call this R3x. Do I know what the error term is? Why not? If I knew what the error term was, I could add it to those 3 and I'd get exactly f of x. So why would I even use a third degree polynomial? I could use a 1 degree polynomial if I knew what the error term was, and I could just approximate things using the error term. You don't know what the error term is exactly. Yeah. Now we can get an upper bound for this error term. So let me just write down some notation here. So what's this P3 mean? What's that P3? What am I calling that? That's a polynomial of degree 3 that's used to approximate f of x. So this is a polynomial of degree 3 used to approximate f of x. Now, of course, if I only use a third degree polynomial, I'm going to have some error. So this thing here has a special name for it. This is the error term, yeah, in using a third degree to approximate f of x. So this is the error term in using a third degree polynomial to approximate f of x. Guys, we have a special name for this error term. What's it called? This error term is called the Lagrange error term. I think it's called the Lagrange error term, isn't it? Lagrange form of the error term. No, we'll just call it the Lagrange error term. The Lagrange error term is like this. Are we ready? It goes like this. Rnx is equal to f. It's the nth plus 1 derivative with the value c substituted in, x to the n plus 1 on n plus 1 factorial. So in this case, Vincent and Nathan, I can actually write some values in for this. I can actually write in this. So this is the general form here. This is the general form for the error. So if I'm using a third degree polynomial, I can actually put my error term on here. What is my error term for using that third degree polynomial? Well, it's going to be this. It'll be the fourth derivative, f4, some value c in it, yeah, some value c, times by x to the power of 4 divided by 4 factorial. Now you're probably asking me, what's this value c? Well, this value c depends on how far away from x that you actually are. What you're trying to do, our job, this is the only thing we have to worry about, Brian, is we need to choose a value c. We need to choose a value c. So if we like, x is going to be an element from 0 up to c. C will be an element of 0 up to some value of x away from 0. And I've got to choose C in order to make this value a... No, I need to choose this. What am I trying to do? My error term is an upper limit. I need to choose C in order to make that as big as I possibly can. To make the largest value of C I can possibly get. Okay, what's the smallest value? Well, the smallest value could be 0, which would make the error term 0. Would that be stupid? Yes, it would be. My error term needs to be as large as it possibly can be. So what I need to do is I need to select C in this range, or in that domain, select C within this domain such that f fourth derivative of C is a maximum. Does anyone see any similarity at all with that formula and something we've done before in this unit on calculus? Does anyone see anything in that formula that rings a bell with something else we've done in this unit? Well, first of all, Brian, where does this come from? I've just pulled it out of the air, haven't I? I've just made it up, really. I haven't told you why or how it works. And guess what? I'm not really going to tell you why or how it works, but very quickly I can show you how it kind of works for a polynomial of degree 0 and how it's related to something else you've already learned. But I won't go on too much about it. What are you going to say? It looks like the... No, we just did it a couple of weeks ago. C should ring a bell. C should ring a bell. Can anyone think of the mean value theorem? What's the mean value theorem? And I'm not going to prove it, but the proof of this is heavily related to the mean value theorem. What's the mean value theorem state? It states f of x, minus, or f of a, minus f of b divided by a minus b is equal to some value f dash c. Oh, f dash c. Hey, this has got something c in it as well, hasn't it? And that's where it comes from. The proof of this comes from the mean value theorem, and it's incredibly long and extensive, and we're not going to do it. But you can get a small window into what I'm saying by doing this. Watch this. What I'm going to do is I'm going to find a 0 degree polynomial. Yeah, I'm going to use a 0 degree polynomial to approximate f of x. Okay, and I'm going to do that at about the point x equals to 0. So watch this. All I need to do here is I go f of x minus f of 0 divided by x minus 0 is equal to f dash c. It guarantees an f dash c, doesn't it? Multiply x by that and add f of 0, rearrange that formula, and I get f of x is equal to f of 0 plus x times by f dash c. Does that look anything like this? Does that look anything at all like that? It kind of does. This is a 3rd degree polynomial, and there's my error term. Yeah? Hey, this is a 0 or a 1st degree, well, it's a 0 degree polynomial, isn't it? And there's the error term. Now, of course, if you like, I could divide that by what? Yeah, 1 factorial, very good. And very, very soon, I think, or very, very quickly, some of you are saying, hey, that is actually the error term if I was to use a 0 degree polynomial. So I can approximate f of x using a 0 degree polynomial if that's my error term. And you can sort of see, just quickly, how the mean value theorem can, in a way, be used to prove what the error term is generally. Am I going to do anything more than that? No. Have I ever seen an error question ever on an exam? Once in 20 exams. So how long should we spend on this? Well, let's spend the rest of this lesson, probably. What's the time now? 45. Well, we might be able to get into the next chapter a little bit. The next chapter is actually relatively easy. This one's a little bit tricky. So how could I calculate the error term? Well, what's the upper bound for the error term if I was to use e to the x to approximate e to the... Can I rub that off? Can I rub that off? As I said, this is in the syllabus, but we don't get many questions on this. Why? It's really tricky. It's really not an easy thing. So, but we'll do it nonetheless, and you'll see it's easy to apply. It's really easy to apply, and I'll show you. But yeah, it is tricky to understand where that comes from. I haven't explained, I haven't gone into depth. That's another hour's work and you'll be asleep by then if I did that. So I always do this very quickly just to show you it's related to the mean value theorem. And that F-C, if you remember, kind of comes from this mean value theorem. And the proof of it is related to that. I'm going to rub that out and show you how easy this is to use. Okay? Rub it out. Let's just do 2 questions, and that's all that I'm going to do. Because I need to do this again when we do the Taylor series, probably on Thursday, which is tomorrow. Ooh. Gosh, we got a bit today. Big day tomorrow, yeah? Yeah, big day. What's that? Well, we've got a double period in class time, and from 11 to 12, and then we'll come back in the afternoon again.
Can we do 2:30?
We can do 2:30 tomorrow or 2:50, or yeah. Well, can we do 2:30? And then we'll just keep going until we almost finish. We will not almost finish, but what I'll do is I'm going to make a video over the weekend. You can watch it over the weekend, and then we'll finish. And then we'll come back next week and start studying past exam papers for maybe, what, 2 days? 2 or 3 days? And then we better have a practice test, maybe Wednesday or Thursday, and then we stop.
Test from 1 to 5 or 1 to 4?
Everything. I'm going to give you an exam. Yeah. So can you hand me your assignment? If you haven't done it, that's it. Can you hand me your assignment tomorrow or today? I'm going to start marking it. I'll hand it back to you on Monday. We'll have a practice test early next, maybe Wednesday, Thursday next week. Yeah, a practice test, which will be a whole exam, and then we've got to stop and start your IAs, and then the following week we'll do it again.
No.
Yeah. But we got to start. Yeah, I know. We've got to really start to get your IAs started. Yeah. Keep in mind, Xavier, it's really important. Just over the next couple of days, this is it. Once I finish this, we won't do any more regular maths teaching until once I come back after the holidays. That's July. So we're almost finished. Isn't this exciting a little bit? We're almost finished for 2 months.
This is your chapter 1, chapter 4.
The whole thing. We're going to do a past exam paper. If you're almost ready, there's no other way. You've got to do these exams in a couple of months, We can't pretend it's going to, let me just do one of these problems. I'll just make it up. Let's say I've got e to the x. I think this is the same one in the book, right? What I want to do, Vincent, is I want to find the error. We all see, here's the question. Find the error in approximating e to the power of 0.75 using a 3rd degree polynomial. Find the error term, right? Let me write that down. So approximate, let me write this down. Approximate, or find the error term. Ready? Find error term. Yeah, in approximating e to the power of 0.75 using a 3rd degree polynomial. What's a 3rd degree polynomial mean? It means x to the power of 3 is the highest order. Okay? So, what am I trying to say here? What's e to the x equal to? E to the x is equal to, this is in your data book, so I don't have to worry about this. E to the x is 1 plus x, isn't it? Plus x squared on 2 factorial plus x cubed on 3 factorial. Cool? Yeah? Plus some error term. This will be R3x. How far, or what's an upper bound? Now, I know what e to the x is, right? Don't you? Your calculator can work out e to the x. Yeah? Because it uses heaps and heaps of terms. But let's just say I was to use e to the x and approximate is how far, what's an upper bound for my error about how far I would be away from that? Does someone want to have a guess? I think we worked it out yesterday. We're about 0.001 away or something like that, yeah? So let's find how we would find that upper bound for that error. What's the formula for it? The upper bound for the error is R3x is equal to f to the 3 plus 1, which is the fourth derivative of c, yeah, times by x to the power of 4 divided by 4 factorial. Great. Okay, so what's x equal to in this expression? What's x going to equal to? X is going to equal to 0.75. So I found what that is. That's easy, right? So really, in this case, we can see x is simply going to equal to 0.75. What's c got to be? Well, c, this is tricky. Sometimes, but what's the domain of c? C is going to be some element from where? 0 all the way up to 0.75. Yeah? And this series converges to the function for all values of x. Yeah? So, what value of c should I choose? Well, that depends on the fourth derivative. What's the first derivative of e to the x? Yeah, what's the second derivative? E to the x. Third derivative, and the fourth derivative is e to the x. So this is an easy one, isn't it? You're not going to get one that easy, so we'll do a harder one in a moment. So the fourth derivative of e to the x is e to the x. So the fourth derivative of x is e to the x. Now what I've got to do is I need to choose a value between 0 and 0.75 to make that number a maximum. Which number will I choose? 0.75. Yeah, that's the hard thing. So I'll practice this again. So I need to make that value a maximum. Vincent? So I need to make this value a maximum. Choosing an x value, that's actually c, Mr. Stewart, you idiot. That's f, fourth derivative of c. I need to choose c from this domain in order to make that value a maximum. And Fee's already told us the right answer. The right answer is f of 0.75 equals to e to the 0.75. So, my error term is equal to, let's substitute all of this in, it's e to the 0.75 times by 0.75 to the power of 4 divided by 4 factorial. Can someone tell me what the upper bound for the error is? I think you can see too why this is an upper bound and not the exact value, because if I knew the exact value I'd add that to these terms and I'd get exactly what it is. Yeah. What'd you get?
2.79 times 10 to the power
2.79 times 10 to the negative 2. So basically, yeah, that's so 0.02, isn't it? 028. Yeah. Which is about what it was yesterday, yeah? That's about how far as an upper bound it's off, yeah? If I was to use a third degree polynomial. Let's do another one out of the book. Let's do a slightly trickier one, yeah? I'll find one for us. So let's find one out of this book, a slightly harder one. Can you turn to page 109? Turn to page 109, please, and can we do... let's do 1C2. Again, use a third degree polynomial to approximate the error in using this. So let's do chapter 2, 4B, 1C2. So we've got 4B, 1C2. Use a third degree polynomial to approximate this. I don't know why we're doing this for, because of course you could just put x equals to 0.5 in and get the exact value on your calculator. But if I was to use a Maclaurin series at x equals 0, yeah, find the upper bound on the error when using Maclaurin series polynomials of a given degree to approximate the following at x equals to 0.5. So you're probably asking, why would I use a Maclaurin series? Yeah? Why would I use a Maclaurin series here where you wouldn't? It's so ridiculous. You just put 0.5 in and work out exactly what f of x is, yeah? But if I was to use a Maclaurin series, yeah, what would the error term be? This is quite tricky, isn't it? Why? Because I need to find the fourth derivative. Yeah, and this is where it gets tricky. So let's actually do that. So the error term using a third degree polynomial is R3x, which equals to f, fourth derivative of some value c, x to the power of 4 on 4 factorial. Now, what's my x value going to be, Xavier? Which x value would you use? Use x equals to 0.5. Yeah. Great. How about c? What c value am I going to use? Well, guess what? We don't know yet. We need to find the derivative, the fourth derivative, and choose a number between 0 and 0.5 to try to produce the maximum number. In most cases, it's either 0 or 0.5. Yeah, that's right. I'm not sure what this is. I hope I've chosen it so it's 0, because in the last one, in this one, we chose this extreme. Let's see whether in this case we actually choose 0 to make the biggest value. Let's find the fourth derivative. There's a bit of work here, isn't there? So let's go. I'll write f of x as 4 minus x to the power of minus 2. Just be careful here, because we're going to have to use the chain rule there, aren't we? Yeah, we've got a negative 2 and a negative 2. So let's go. First derivative will be minus 2 times by minus 1, 4 minus x to the minus 3. Next derivative is going to be, well, that's 2, so that will be minus 6. Got to be careful here, don't I? That's minus 6 times by minus 1. Yeah? They're all looking like they're positive. So that's minus 6 times, that's 6 times minus 4 is minus 24, times minus 1 is 24. Yeah. So I've got minus 24. No, I've got 24. Mr. Stewart, what are you doing? Is that right?
Yeah.
The fourth derivative is going to be, right, this is a bit, what's that, 100, 120? Is that what you got, Brian? So let's write this down. Yeah? So I've got the fourth derivative is going to be 120 divided by 4 minus x to the power of 6. What value of x do I need to choose? I need to make this number as small as possible, don't I? Which will give me a bigger number. So, yeah, I'm not going to use 0, am I? I'm going to use 0.5, yeah. So this is going to equal to 120 divided by 4 minus 0.5 all to the power of 6. Come in. It's good to see you back. This is the last. Although I think we'll keep making videos, won't we?
Yeah, that's good.
Yeah. Well, come in. It's lovely to see you back.
The number is
I
back.
know everyone missed it.
Yeah.
Yes, it's good.
No, we didn't. No, it was so noisy. It's so noisy in that now. No, it's okay. Good to see you. Yeah. Will we work this out? What's the error term, Brian? So my error term is going to be, let's work it out, R3x is equal to this here, which will be 120 divided by 3.5 to the power of 6 times by 0.5 to the power of 4 divided by 4 factorial equals to, what's my error term?
Yes.
4b it is. Let me just check the answers. I just want to see if we're getting the right answer here. Not that it matters, it's quite possible the answers in these are wrong. 4b, what do you get? 1.7 times 10 to the minus 4? Yeah, so we end up with 1.70 times 10 to the minus 4. Okay, same as the book. So that's the upper bound for the error. Now, why would you do this? You'd never do that, would you? Why? Well, it's just easy to get the exact value. Why would you use a third degree polynomial to do that? You just wouldn't do that. Of course, for sine, you would, because how else do you get the value for sine? How else does your calculator get the value for sine? It uses a Maclaurin series. For e to the x, how else does your calculator get the value for e to the x? Uses a Maclaurin series. How else do you get the value for pi? Do you know there's a Maclaurin series for pi? Otherwise, how does your calculator know? How does your calculator know how to get sine of 1.234578? What, it's just in there? Every single value of sine's in your calculator? No. It just uses a series to do that. That's all it does, yeah? It's already pre-programmed in, and that's how your calculator does it. Of course, your calculator doesn't have infinite values of sine in there, does it? It needs to use an algorithm of some sort, and so they use these algorithms to work it out. Probably not exactly, I don't know, but you know, something similar to this. Can we do question 4 as well? Because what's the time? 3 o'clock?
Yes.
Yeah, oh, we've got heaps of time. So we can we keep going? Yeah? Can you have a look at question 4? I looked at this before I came into class and thought, that's interesting. I would like you to, well, I'll set some homework tonight, but I don't want to do too much on this. But there's a couple of good questions there. Can we look at question 4? Let's see if we can work out that one. To me, it looked like there was an error, a mistake in question 4. But it'd be interesting to see if there is or there isn't. So I'll just rub off this. I wasn't sure if there's an error in question 4 or not, or I just... That's all I'm going to rub in. No more. I'll write down question 4 on the board, and we'll see if we can work it out. Welcome back, Om.
Thank you.
Good. Welcome back. Really lovely to have you back.
I know.
I bet everyone's been saying that.
We started singing.
I'm only pretending to be nice. No, it really is nice. Now we won't have to. It's good. It's really good. Right time to come back too, isn't it? I think there's a lot of. I saw there's a lot of Year 12s back as well. Like Yannick was down there. Samar was down there, wasn't he? Rain's been coming in, so I think you find a lot of the locals will start coming in, but it's good. Right, what do you think about this? It said show this. How do you think I might show that? Show that that is less than that. By the way, just before we go, is the error term absolute? It is, isn't it? The error, I think it's absolute. I mean, error terms are absolute, so don't be shocked by the. Where do I start here? Do you think? What would you do? This is clearly like, it looks like, these things look like e to the x, don't they? But do you notice what's missing in here? I wasn't sure if this was a mistake or not. Yeah, it looks like it's a mistake. Now, I just thought I'd explore this with you. I'm not sure if it's a mistake in the textbook or if there's another reason for it. So I thought, well, let's just do this in class, even though it's dangerous. But let's just see if we can work out maybe if it's a mistake or not. Okay? I don't know. But I thought I'd do this with you so we can just, you know, kind of play around with it. There's the question there. So I'm thinking, of course, we'd start with this. E to the x is equal to 1 plus x squared on 2 factorial, yeah, plus x cubed on 3 factorial plus an error term, isn't it? R3x. Yeah, now what's R3x equal to? What's my error term? So the formula for my error term, R3x is equal to the fourth derivative of c times by x to the power of 4 divided by 4 factorial, isn't it? Yeah. Does that help us? For x less than for the absolute value. Now they have put a limit on it. They've said such that the absolute value of x is less than 1. Yeah? So the absolute value is less than, so let's find the largest possible error term, shall we? Yeah? So such that it's less than 1. So I'm going to put 1 in there for that. Yeah? And I'm going to put 1 in here. So what's the fourth derivative of e to the x? Is e to the x, isn't it? And then I'm going to divide that by 24. So if I was to find that using, yeah, the absolute x was allowed to be anywhere between it, I just needed to show that. So I'm going to write this as e to the power of 1 times by x divided by 24.
It should be times x to the power.
Yeah. But however, I've just let x equal to 1. Yeah? So I've let x equals to 1. So I've just got that really, haven't I? Yeah. So if I was to go this one minus that, to me it would be, oh okay, so e on 24, e is smaller than 4, so that's going to be less than 1/8. No, well e is smaller than 3, isn't it? E is 2.7, so I'm dividing that by, no, that's bigger than 1/4, isn't it? That's bigger, that is slightly bigger than 1/8. No, it's smaller, yeah. So that works, isn't it? Yeah, so I think that's where that comes from, agreed? So now we've got to make some sense of this. So really, this is an upper bound, isn't it? Yeah. So this might, I reckon they forgot to put in there x. Don't you agree? I think that's missing. Good. Which is what I thought when I saw the question. I think the question's wrong. I think it should be e to the x minus 1 minus x squared on 2 factorial minus x cubed on 3 factorial will be less, yeah, because that's going to equal to, what's that going to equal to? That will equal to r3x, which is less than 1/8. And so if we just take the absolute value of everything, yeah, then that's what that's going to be. Well, the error is an absolute value, isn't it? Okay, so I reckon that's how we prove that. So it's a mistake in the book. Good. Yeah. What was one of the conditions? I might just do this quickly. What was one of the conditions such that an infinite Maclaurin series is precisely the same? So, yeah, that's just an example there, but you can see these are quite tricky, aren't they? Yeah? That would be really hard to do in an exam, wouldn't it? If you didn't know that we were dealing with errors, how would you know how to do that in an exam? Almost impossible, isn't it? Yeah.
Why did you let c equal 1?
Well, the question, if you just read the question, they're saying such that x, the absolute value of x is less than 1. Yeah. So x is between -1 and 1. So I just thought, well, I'll just take the extreme value and make it equal to 1. Yeah. Because that will then make it bigger than what it needs to be. So I'm just going to take 1. Yeah. So I let x equals to 1. Why? Because that will produce the biggest possible error. Yeah? If I let x equals to 1, it's going to produce the biggest possible error. So the biggest possible error it could be would be when x is equal to 1. So I let x equal to 1 there. And then I chose the fourth derivative of e to the x is e to the x. So that just becomes e to the power of 1 times by 1 divided by 4 factorial. Now, it just so happened that looking at this, that's very close to 3, isn't it? It's slightly smaller than 3. So, if this was 3 on 24, that would be less than 3 on 24. Agreed? So, e on 24 is actually less than 3 on 24, which is equal to 1/8. If you got that in an exam and they didn't tell you what that was about, you would struggle to work this out, wouldn't you? You've got to know it's a Lagrange error term. You've got to use Maclaurin series. Oh my gosh, like without any sort of prompting, you'd be in a lot of trouble with that sort of question, I reckon. Anyway, I've got one more thing I want to show you before you all go to sleep, and that's, what did I talk about at the start of the day? When does a Maclaurin series, an infinite Maclaurin series, equal to the function? When is an infinite Maclaurin series equal to a function? When the values of x you're dealing with are within the interval of convergence, which we've already talked about, that's obvious, of course. We've kind of dealt with that in chapter 3. But it's also when my error term would be equal to, if I kept going on and on and on and my error term was 0, what would you say? The series was exactly equal to the function. So again, I've never seen this in an exam, but let's just do it once and then let's move on, yeah? Yeah. So how do we prove that the series for e to the x is exactly equal to the function? But just first let me write down the theory or the theorem or the rule. Brian, can you read it out? What is it? What does it say? I'm on page, it's key point 4.4. Key point 4.4 on page 107. What does it say?
The infinite Maclaurin series for fx is precisely the same as the function fx.
Yeah, so the infinite, got it, Maclaurin series for f of x, is, what did it say, exactly equal?
Yeah.
Is exactly, interesting terminology, well, why not just equal Equal is exactly equal, isn't it? Now, why they've used exactly equal? Do they really use exactly equal?
It's precisely the same.
It's precisely the same. Yeah, okay. I like that better. Does anyone know the symbol we use for precisely the same? There's a symbol we use equals for equals. Does anyone know what precisely the same symbol is? I think, isn't it 1, 2, 3? Have you seen that before? With 1 on the top, is it? Yeah, it might be 2 with a little squiggle on the top, isn't it? Yeah, is it this one here? Precisely the same. Yeah? Is that what they've used it in the book?
Oh.
Yeah. It's precisely the same as the function, f of x from which it was derived. Do they say from which it was derived? Anyway, it doesn't matter. So what they're basically saying, the infinite Maclaurin series is precisely the same as the function for which it was derived when this is true, when the absolute value of the error term as the limit as n approaches to infinity is actually equal to 0. Basically that means there's no error at infinity. Now, you would think that would always be the case, wouldn't you? You would think that if you were within the radius of convergence, I'm not sure if this is going to make sense to you. If you were within the radius of convergence, you would think that the Maclaurin series would just equal to the function, wouldn't you? As long as you take enough terms. But that's not always the case. But I've never seen a situation where it's not always the case. It seems to be always the case. Yeah? Once you're within the radius of convergence, it's fine. So let's just do a situation to show where that's a situation. Does anyone, let's just do it for e to the x, because we've done this for e to the x. I just want to do one example here. Maybe I'll set one for homework. Yeah? But let's just do one example where we've got f of x equals to e to the x, and my Maclaurin series for e to the x is 1 plus x plus x squared on 2 factorial plus x cubed on 3 factorial plus dot 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 dot, and my Maclaurin series for that is the sum from 0 to infinity of x to the power of k divided by k factorial. Yeah? So, what I need to do, so there's my series. What I need to do is show that my error term at infinity is going to equal to 0. So what's my error term for this series? So what's Rn equal to? And this is why this can be quite tricky to prove. Rn is equal to f to the power of n plus 1 times some value c, yeah, times by x to the power of n plus 1 divided by n plus 1 factorial. Now, what's the nth plus 1 derivative? What's the n plus 1's derivative of f of c? E to the c, isn't it? Yeah? So this is going to equal to, now, what we're going to do is take the limit. Ladies and gentlemen, this is absolute value. I now need to take the limit as n approaches to infinity of this term here, which is f, the nth plus 1 derivative of c, x to the power of n plus 1 divided by n plus 1 factorial. Now, this derivative here, that derivative here is e to the x each time, but I've got to put c in for x. So that's going to equal to, the limit as n approaches to infinity of e to the c times by x to the n plus 1 on n plus 1 factorial. Ladies and gentlemen, what's e to the c? E to the c is just a constant, isn't it? So we can take the constant outside of my limit sign, and I'm left with this. E to the c times by the limit as n approaches to infinity of x to the n plus 1 on n plus 1. Can someone have a guess what you think this limit is equal to? In an exam you're allowed to say this, you don't have to prove it, it's quite tricky to prove. That limit equals to? 0. Yeah, that limit there is equal to 0. So what does that mean? It's going to approach 0. So yes, the infinite Maclaurin series is equal to the function. The way they do it in the textbook though is a little bit more tricky. So don't panic. The way it's done in the textbook, if you have a look at this is the way they do it. They say this, they go e to the c times by the limit as n approaches to infinity of n to the x plus 1 on n plus 1 factorial is less than or equal to some constant m times by this limit. I don't know why they do this for, and of course you're allowed to say, ladies and gentlemen, that this limit here equals to 0. So this is less than 0, so using the squeeze theorem, that's equal to 0 as well. Okay, so we know, therefore, basically, the limit as n approaches to infinity of r to the n is equal to 0. What does that mean? If my error term at infinity is 0, it means the function is precisely the same as the infinite series.
Mr. Stuart, why that one is equal to 0, the limit as n approaches to infinity?
Of this,
Yeah.
that's really tricky to show that.
But do you have to show it?
No, you're allowed to use that in an exam. What are you allowed to use in an exam? This is you're allowed to quote this, and I'll just write it up here. Yeah. So the limit, ready, as n approaches to infinity of x to the power of n divided by n factorial is equal to 0.
This one you just try to prove this one, or is it just a question?
Yeah, I'm just trying to show that an infinite series is equal to a function when, or precisely the same as a function when the error term is 0 at infinity. So all we've got to do is investigate the error term as n approaches infinity and show that that's equal to 0. If it's equal to 0, we're allowed to say that the Maclaurin series is equivalent to the function. Now, you would have thought this, and I've never ever seen a question ask this ever, but you would have thought that's the case anyway, wouldn't you? Yeah, if you add on more and more terms and those terms are getting smaller and smaller, but that's the only situation where that occurs. Perhaps but it must approach 0, not a constant limit. I can't think of an example where that occurs. So that's enough for today. We're not going to get everything finished, ladies and gentlemen. We'll try our hardest tomorrow. I think we'll get we'll be one class away from finishing, but I think, if you don't mind, I might make that on the weekend. I might make that and send that to you. Yeah? Or we can do it on Tuesday, because I won't be here Friday or Monday. Perhaps not, I'm not sure.
So you'll not be on this one?
Yeah, or on Monday. So, yeah, so this Friday. So that's why I'm trying to get all this done now. Yeah. So, so you got Friday off if you like. Homework. We have a double, and then we'll have a period in the afternoon. And we will be very close to finishing. I think we'll be one period off finishing, and I think I can make a video on that so you can watch that in your own time on Friday. Yeah. And then, look, there is a good chance I'll be here on Monday, so we'll see. Yeah. Hang on, I'll just switch this off because everyone's here. They don't know that.